Everyone, I'm Susan Nash, AAPG, and we are here for AAPG Academy. We have a fantastic presentation today and wonderful topic with Dr. Paul Mann of the University of Houston. And before he gets started, I just want to take a moment to thank our sponsors. So I'm going to share the screen and go to NewTek Technology Energy Company. And I'm so excited about having a sponsor because we are able to continue to offer this webinar free thanks to NewTek. So just want to mention that NewTek offers petrophysics and dynamic modeling. They do resolutions of thin beds, silty reservoirs, textural grain size, pore size, triple combo data set to provide facies and pore size distribution. They've done work for Chevron and frac modeling for fluid efficiencies and 4D reservoir modeling. So I really want to say thank you to NewTek and I encourage you to contact them. We will send you an email with their contact information after this. And also, if you would like to be contacted by NewTek, please indicate so by sending me a direct message. I'm Susan Nash. So at any rate, what I'd like to do now is invite Paul Mann to share his screen and to say welcome. And then also just maybe he can introduce himself a little bit and his research interests that he's working on now. Perfect. Okay. Thank you. Thanks for helping. So this is fine because people are still joining. Okay. And if you're just now joining, I would just like to remind you that you will receive an email from me after this is over, and it will have a link to the recording. And I'd also like to remind you that if you are interested in finding out more about our sponsor, please send me a direct message. So thank you and welcome, Dr. Mann.
Okay, great. Thank you, Susan. And welcome everyone to this Academy on Deepwater Exploration. So I'll be talking to you for the next 40 minutes or so on different areas that we're working with at the CBTH project at the University of Houston. Okay, so just to go through the talk outline, we've got an introduction. I'll talk a little bit about our project. Then I'm going to go and talk about the correlation of rifted passive margins with hydrocarbons. Then talk about non-volcanic versus volcanic margins and what how those impact hydrocarbon exploration. And then get to some basic stuff like how does a non-volcanic continent ocean boundary form? So this is really fundamental to the area that we're working in, which is this very deep water areas. And then finally, I want to apply all of those numbers 1, 2, 3, and 4 to other areas. And these are sort of emerging hydrocarbon areas, Guyana, West Africa, Brazil, Namibia, and other places. So just to get started, though, at the bottom part of this slide, you see a ion, which is now TGS image of the Black Sea. So on the left here, you see a rifted conjugate margin, continental crust, and then on the right, you see the other part of that rifted conjugate margin. In between, you see ocean crust. These circled areas are what we call the continent-ocean transition or boundary, COB. So I'm going to be talking a lot about these particular areas in terms of their hydrocarbon potential. Okay, before I get started, I want to say a few things about our project, because this is a group effort that's involved a lot of people over the past couple of years. Shown here are some of the students and researchers that are part of this project. I'm not going to go through them individually now, but I will introduce them as I talk about their work. I'd also like to thank our sponsors down in the bottom left who provide our support for the project. And I'd especially like to thank our data providers shown here on the bottom right, where we develop and use their data. And a special thanks to Andy Pepper and Jean-Marie Legel. I'll be talking about their Excalibur Basin Modeling Program a little bit later. Okay, so just to get started, where are the rifted passive margins on Earth? And shown here in this map of the world, you see the green areas, these are the passive margins. Shown here, the red areas are active margins. So the difference is that passive margins are rifted margins that are now passively subsiding, whereas these active margins are either subduction zones, strike slip boundaries, or other forms of an active plate boundary. So you can see that the Atlantic is one of the largest areas of rifted passive margins, this area in here. But notice this sort of wedge shape. This wedge shape started opening back in the Jurassic Cretaceous time. And as it opened, that moved Africa, India, and some of these continents into what used to be another wedge shape, Tethys, which is now closing. So Tethys has become an active margin, while the Atlantic has become a passive rifted margin. And these stars here represent earthquakes. So these are areas that are all tectonically active. So today we're going to focus on these margins in the Atlantic and the Gulf of Mexico, which pretty much have formed since the Jurassic to the recent time. So again, breakup of Pangaea breaks this supercontinent here. As it opens up, it closes Tethys over here. And so that's how we end up with the present day distribution of passive margins. Okay, so one of the themes that we're going to talk about today is moving from on land, shallow water into deep water. And we know this living here in Texas. We have over 1.4 million oil and gas wells drilled in Texas, these black dots. So over the last 100 years or so, there's been a migration from on land into the shelves of the Gulf of Mexico and now into the deep water Gulf of Mexico. And we'll see the same pattern happening in other places now, like the South Atlantic. So this is a compilation on the right by Dolson et al. 2021 of giant oil fields discovered since 1868. And you can see they're color-coded by the reservoir type clastic carbonate basement. But notice the yellow type, the clastic types in this area of the Atlantic. So these would be giants discovered over the past, the most recent phase would have been since about 2010. And you can see that a lot of these big discoveries are happening in places like the Gulf of Mexico, Guyana, West Africa, and the other parts of the South Atlantic. So again, we have this pattern moving from the land areas. This goes back to 1860, right up to the present. But you can see about 1980, there was a divergence where we get into deep water discoveries and ultra deep water discoveries below 3,000 meters. But we continue on land and Permian and other places. But so we have this sort of bifurcation starting about 1980. Okay, so one of the really fundamental parts of these rifted passive margins is the question of, are they volcanic or non-volcanic? So on this map, I've color-coded volcanic as red, non-volcanic as green. And what that means is these red areas are characterized by this effusive outpouring of volcanics during the rifting process, whereas the green areas are not. So notice we've got the South Atlantic. The southern part of the South Atlantic is very much a volcanic margin. Then we get into the non-volcanic margin of Brazil and its conjugate in West Africa. And then we get in, this is actually mistakenly drawn here. This should be green. This part of West Africa is non-volcanic. The east coast of the US is volcanic. In our view, Gulf of Mexico is non-volcanic. And then we get into a non-volcanic area in this North Atlantic. So why is this happening? Well, one idea is that in these areas where trends are more or less parallel, and by trends, basement trends, this breaks easily and forms a more effusive and a better conduit into the mantle. So you get these volcanic margins, whereas here we have trends in the older orogenies that are cross-cutting, and therefore that's harder to break. Mantle is less involved, less volcanism. So that sort of alternates back and forth. Notice here we're cutting across the Appalachian Caledonites, whereas here we're parallel here we're sort of half and half, and then here we're cutting across trends. So that's just a really basic ideas about why we have volcanic margins. But one of the important things is notice the correlation with the giant oil fields, which are shown here by these black dots. So generally the non-volcanic areas are more prolific in terms of hydrocarbons. But, that's changing. And I'll talk about how some of the big discoveries down in the southwestern part of Africa are challenging that idea. So how do these margins look like in cross-section? So this is the sort of schematics from Franca 2013, just showing a non-volcanic margin up here and a volcanic margin. So obviously the volcanic margin has this area of what we call SDRs, seaward dipping reflectors. These are large flows that have propagated out during the rifting process and sort of infilled an area which in the non-volcanic margin would be filled by sediment. So these volcanics are filling a lot of the available space that normally in a non-volcanic margin would be filled by sediment. So if we look at some areas here, this is the Gulf of Mexico, we see non-volcanic, we see a lot of sediments, we see salt, we see a breakup unconformity, but none of these type features are obvious, at least at this scale. If we go down to Namibia, we see these features, SDRs, forming the basement to the large discoveries, which I'll talk about in a little while, the Venus and some of the other discoveries, which notice that all of these source rocks and reservoirs are perched on top of the SDRs. So this is challenging the idea that these volcanic margins are not prolific oil producers. Okay, so, and then just a few other examples, though, of these non-volcanic margins. Again, the Black Sea and volcanic margins are a question of degree. There's always going to be some volcanism around, but not in the prolific way that we see for a place like Namibia. So we would call this a non-volcanic margin. We go to the Gulf of Mexico. This would be the northeastern Gulf going from Yucatan up to Apalachicola area. You can see oceanic crust, moho. You can see the spreading ridge out in the center. It has a little volcano right in the center of it. And then the moho over here. And notice the margins. These are what I'll call marginal rifts, which I'll talk about later, filled with salt, but no obvious SDRs like we see in a place like Namibia. Okay, and again, speaking of Namibia, this would be a line from TGS published by Winter et al. But here you can see again these what we call seaward dipping reflectors forming the base of all of these big new discoveries now that are happening in Namibia, the Venus and the Graph happening at different levels above this sort of basal volcanic sequence. Okay, so one important point then, just to kind of wrap this up, is what is the relation of these settings to hydrocarbon potential? And again, these are giant fields. This is an older compilation, only goes up to about 2000. But basically what we did back then was we counted up all the giant fields. There were about 900 of them. And we found that about 2/3 of them were either in rifts or passive margins. The rest were in collisional zones, strike zones, subduction margin, but those made up a much smaller group than these two together. So that's the main sort of summary here, is that rifted passive margins are really the place to go for oil and gas accumulation. And why is that? Well, these are passive areas. In other words, they're not being actively deformed. Remember, this area here is opening. Tethys over here is closed. This is a very active area. And so oil can be more easily disrupted, can leak out in this type of sort of reactivated deforming area. And we can see here on this plot from McGregor, most oils are pretty young, Cretaceous to Tertiary, because the older ones just have trouble surviving all of this deformation that's going to happen to them eventually. Okay, so a couple of other sort of just housekeeping things about rifted margins. You hear this term taper tapered margins. It just refers to whether it's a low angle taper like this one here, or whether it's something much steeper like this one down here. So the low angle type tapers are what we call orthogonal rifting. Like, for example, the Central Atlantic opened at right angles to this arrow here. But if we come down to the Equatorial Atlantic, it's different. It's oblique opening. So here, where we have orthogonal opening, we get this very thinned out margin, like in Iberia and other places. But if we come down to a place like Ghana, and here you see a very truncated margin, ocean crust, very truncated, and then we have some transtensional features forming back behind there. So really basic difference in rifted margins. So one other feature that I mentioned earlier, continent-ocean boundaries. And I just want to take a minute to talk about how those form. So if you think about it, we're going from thin continental crust, shown here in the brown, the mantle is green, to ocean crust down here. So how does that happen? Well, one idea, and Mark Rowan and others have talked about this also, is we have what we call marginal rifts. So we have a central rift axis here, shown with this black being evaporites, it's filling it. And then at some point, the ocean crust sort of pokes up and it divides this central rift into two marginal rifts. So they're basically half of a rift on either side. And then these two marginal rifts get pushed aside as the ocean crust widens. So how does that affect hydrocarbons? Well, if we look at a place like Perdido in the northwestern GOM, we see what's called the step-up fault. So the step-up fault forms during this period when when you're intruding this ocean crust, which is going to sit higher than the surrounding marginal rift. So you have to step up to get to it. So over here would be this marginal rift, and over here is the ocean crust. So we're stepping up, and then all that got reactivated during the passive margin fold belt of the Perdido, and produces all this folding. So the step-up faults, you see them in other places. Here's one in the Congo, where you're down low here, and then you're stepping up to ocean crust. Again, we think this is reflecting this rift that's split into two as the ocean widened. Okay, so just a little bit more on basic rifting. Talk about the Red Sea. So the Red Sea, I call it how to make a rift in 25 million years, because it's the youngest continental rift that we have, that we can actually see what's going on in terms of how the continent ocean boundary is forming. So a couple of things about the Red Sea. It's opening about a pole in the north, so it's opening faster in the south than it is in the north. The northern areas rifted continental crust. There's a break here at the Zagreb fracture zone, which marks the beginning of the continuous oceanic crust. And the basin was transgressed about 14 million years ago, so it has salt. And some things that are happening, you can see pretty clearly on these maps. It's very symmetrical. The rifts and the spreading ridge run right down the center, so there's no upper plate, lower plate, or any of that kind of stuff. The salt is being split by the ocean spreading that's going on here. We see that in the Gulf of Mexico and other places. So that means all of the salts is sitting on rifted continental crust, and then the ocean crust is going to come along and split it into two halves. So keeping those in mind, just a few examples, and this is some work by Mohammed Abdel Fattah, who's a student with us. Here's the line. These are blocks, normal faults tilted towards the spreading ridge, which would be off in the center here, or the master rift, since we're in the northern continental rift area. Salt has come in. There's sort of a swelling as you approach the center line, which are these black dots. They call them the deeps. And then if we move to the south down here, we can see that this process here has given way to the formation of oceanic crust in what's called the Thetis deep, which is these black dots down here. So again, the ocean crust has sort of upwelled and split the continental crust into two, and as this continues to open, this will widen. So again, the salt, which is kind of this red area, is getting split down the middle by this rift process. And there's deepening going on too. So what was used to be shallow water is now being replaced by a deeper sort of central line down the middle of the basin. And we see this same process having happened in the Gulf of Mexico, where we have the Luan and the Campeche salt was split by this Jurassic spreading ridge. If we look at magnetic data, you can see this is continental crust here. There's the marginal rift, this kind of low that runs along here. And there's the continent ocean boundary with the oceanic crust to the north. So this would be the step up area. Okay, and then one final sort of housekeeping thing is salt, because that is an important factor for Brazil, Namibia, some other places in the South Atlantic. So again, back to the Triassic-Jurassic time, we have the breakup of Pangaea, this huge magmatic province called Camp, Central Atlantic magmatic province, forms over a very broad area. As you split the continents apart, they're actually surrounded by an ocean. It's called the Panthalassia Ocean out here in the west, and then Tethys is over here to the east. So you're going to leak water into this broken up area. So they're basically, the salt's going to run along these marginal rifts that I just talked about. You can see the red color here, the salt. So this is coming in from the Tethys. The Gulf of Mexico, we think it's coming from the Panthalassia Ocean out here. Why? Because it's thick here, thin here, thick here, thin here. So it's thinning to the east. If we come down to the South Atlantic, this would be younger period during the Cretaceous, thick salt, thin salt, thick salt. So you can see that it's a seepage effect during the breakup of Pangaea. So, and just a reminder, this salt's going to be really important for the big oil discoveries in Brazil and over here in West Africa, because it's forming the seal. Not so much subsalt has gone on up here, so we don't really know the whole story if there's another subsalt area waiting to be found up here. Okay, so like I said, getting to the kind of applications of this information, I'm going to go through these areas: Guyana, Surinam, Equatorial Brazil, Campos Santos, Niger Delta area, West Africa, and then Namibia. So the things that I'm going to kind of point out as I go along are, is it a volcanic versus non-volcanic margin? Was it open orthogonally or obliquely? Where is the COB? And on this map, the COB would be this white line that we've drawn in here. Is there a marginal rift, like I described earlier? How thick is the continental crust? So that's going to affect its heat flow. Is it syn rift or post rift source rocks? Is there an overburden, and how thick is it? Is there salt or no salt? And then trendology, we've compiled all of these wells, and these green dots represent oil wells. The red dots are gas, and the yellow is mixed gas oil. So what are all these previous wells that have been drilled? What do they tell us? So these are the points that I'll hit on each of these areas. Okay, so starting out Guyana. Guyana is the success story of the decade, discovered in 2016, producing since about 2019. 10 to 30 billion barrels of oil are expected. So where is Guyana? Guyana is at the boundary between the Central Atlantic, which mainly opened during the Triassic-Jurassic, and the Equatorial Atlantic, which mainly opened since the Aptian. So it's at a boundary between two different ocean basins. It's also marked by this feature, the Demerara Plateau. This is a large, we think this is a hotspot track, as others have pointed out, that connects it back to the Guinea Plateau, which is over in West Africa. So these are connected by this kind of diffuse hotspot track, and the ages of these intrusions are shown by the numbers here. So we're at a boundary between the two. We're in an area of old crust in here. We think this crust could be Jurassic, most of which has been subducted below the Caribbean. Okay, so again, Suriname, or Guyana, Suriname are at this point here, 2023, and the growth here in oil is considered considerable up through the end of this decade. Okay, so what about the subsurface of Guyana-Surinam? So this is a 3D gravity inversion crustal thickness map made by Kenneth Schipper, one of our students. And what you see here is the Guyana Shield, this area out here. These are cross sections across the what we call the necking zone, which is the thinned area of continental crust. And notice these very regular lineaments here. This is what we call the Guyana Rift. This one's called the Nickerie or Comoline Rift, and notice they wrap all the way around the area. If we look at cross sections through there, it's a very thinned out margin. It doesn't have this feature here. But we consider this northern part a non-volcanic margin, whereas this big promontory here, the Demerara Rise, this is the hot spot that I just showed you a minute ago. This is a volcanic margin, but very localized. You can see it transitions very rapidly both to the south and to the north. So again, we're transitioning from the Demerara, this pink area over here, to a non-volcanic margin up in Guyana. And notice that a lot of the discoveries are right near this border between the two. So again, we're at the border between the central and the equatorial Atlantic. And so you really have two rift phases. You have an older rift phase, which created the margin, and then a younger rift phase that comes in the Cretaceous on top of this older rift phase. So it's a kind of a complicated story where you end up with two rift phases and two passive margins. So again, the hotspot history is important because it shows that the Guinea Plateau is its conjugate. The hotspot shows that this kind of flexure that we see on both margins is related to the load of the hotspot. And in Guyana, the sweet spot is right in this flexural low that's generated just to the north here, near the border between Guyana and Suriname. So that became a sedimentary conduit. And if we look at their stratigraphy, this is Guyana on the right, Mauritania on the left, which is just north of the Guinea Plateau. Very similar with the same unconformities, the same carbonate history, more overburden in Guyana. Okay, so a couple of more lines just to show this, what we consider the rifted structure of Guyana. This one's in northwestern Guyana, southeastern Guyana. If we look at the LISA well published by Price et al., you can see that LISA really only penetrates the upper passive margin on the equatorial Atlantic. So it's really only getting down to the upper Cretaceous. And yet we still have this whole history beneath there of this earlier rifted margin. Okay, so another question though that in Guyana that's important is, does the COB determine the seaward limit of petroleum? In other words, if you look at a map like, let me go back, like here, for example, we have the COB. So we know this is ocean crust. This is ocean crust. Do we need to explore out there, or is it too cold? And this diagram here just shows that where you have a continental block, you have radiogenic heat production, which is very high. But if you're on ocean crust, it's much cooler, especially if you're far from the ridge or you're in an old area of ocean crust like we have in Guyana. So the question then is this what we call radiogenic heat production of the continental crust a requirement to make productive areas out here? Here we see green dots, those are productive wells. Red dots, those are mixed gas oil. And then we got dry holes out here on what we think is ocean crust. So it becomes a modeling exercise to see if there's enough heat coming out here in order to be able to generate hydrocarbons. So Kenneth has carried out a modeling study where he's modeled the continental versus ocean crust transition out here, and it's roughly between the productive area and the dry holes. And the idea, though, is to de-risk exploration in this part of Guyana and Suriname. So there's the COB, and you can see there's a couple of productive areas like the Ranger well, but there are quite a few dry holes also. Okay, so the benefit of this is to try to to project these trends into other areas. Obviously, does this productive trend come up here? Does it stop? Does it maybe go off in a different direction? So the way this is, he's working on this now is using Excalibur software. And I mentioned earlier, Jean-Marie Legel and Andy Pepper have been developing this, but it's basically a faster way to compute a lot of the parameters that are used in basin modeling, which can then be applied to regional scales. And so one of our goals of our project is to use Excalibur over the entire Atlantic margins, not just individual areas. So just some results from his modeling. This refers to the standard thermal stress. So the hotter colors are the sort of hot areas. The green colors are the cooler areas. And you can see that where you have the warmer areas, you get into some gas fields here. Where you get out of the hotter area, you get into oil fields over here. And then a lot of these areas are not that well explored to really see how this model is going to work out, although it does have a predictive capability. And again, not showing a lot of heat out here on the ocean crust. There is more heat as you get into more sediments up here, but this is generally a cold environment. And then we've combined this with some work by Vinnels and Combrick, which were just outlining some reservoir areas around and trying to just get a feel for how this might project into some of these other areas. Okay, so moving on now from Guyana-Surinam down to Brazil. So Surinam or Brazil border would be roughly here. This is the mouth of the Amazon, Aranhas Basin, Ceará Basin, and then it kind of turns the corner here. So this is what's called equatorial margin of Brazil. So again, COB is important, and we've compiled the COB, the white line from Mueller 2019. That's the G plates group. And we've added our own COB, this red line, and that's based on some of what I'll show you in a minute. But we think it's actually a broader COB than Mueller and others had thought. Mueller and others were mainly going off the satellite gravity data, while we're trying to use more seismic reflection data. So starting with the Aranhas Basin here, and again, just basic observation. This formed in the equatorial Atlantic. It's oblique opening. And you can see how the faults are sort of oblique to the margin. It's a narrow margin. It's a steep margin. It has a passive margin fold belt on it, which is typical of a steeper transform control margin. It's got rift features, though, that are all through this very thinned out crust, which almost looks like mantle exhumation if this line were longer. So again, we're pushing the COB to further out in the basin, just based on these observations here. And not a lot of wells. There's one well here, but no one has really tested very much this deeper part out here. So that would be interesting with potential source rocks in these half province. And then this is just looking at the one of our geopost lines, but you can see again this non-volcanic rifted margin. You have a kind of a sag on top of it with Albion or Aptian source rocks tests are proven in these wells here, and then you get up into the passive margin. So there's both sag prospects with the sag and onlap, but there's also prospects within this lower rifted section. Okay, so moving now to West Africa. So this would be the conjugates to the equatorial Brazil. So we have Ghana, Niger Delta, Equatorial Guinea, Gabon. And again, the white line here is the Mueller COB. The red line is the COB we're proposing. Notice it's a lot wider in our view in the Niger Delta than shown by Mueller et al. And again, the colors represent gas wells, oil wells, and then yellow is mixed oil and gas. So you can see this area has a lot of promise. There's been a lot of recent discoveries here, and we're thinking there's a bigger play fairway in this area than previous people have thought. But I'll show you first some things from the Niger Delta and then some things on the Equatorial Guinea. So the Niger Delta, the reason why we're moving the COB seaward is this magnetic map. So you can see these lineated features here. This is typical of ocean crust. You can see the fracture zones here, and then they suddenly stop here. Our new proposed COB is this white line. And notice these anomalies over here are quite different. Very broad amplitude anomaly, very typical of continental crust. In fact, this is a old Paleozoic fold belt between the West Africa craton over here and the Congo craton over here. So it's truncated by the rifting almost at right angles. And then we also have some gravity modeling. By the way, this is work done by Jumoke Akinpelu on her study, but she's working on trying to better define our new proposed COB. Okay, so moving now to Equatorial Guinea, which is to the southeast of the Niger Delta. Small country, but it seems to have a lot of potential just based on what we've looked at. These are data provided by GeoX. But it's a very steep margin because it's a obliquely open margin, so it has a tendency to form passive margin fold belt. It has a lower rifted section in continental crust. You can see that here. It has a little bit of salt. If you remember the salt map where salt had percolated up to about this latitude from the south, the Aptian salt. So it has source potential, reservoir potential, seals, all in a fairly small area. And one interesting thing about it is it gets into ocean crust pretty rapidly. And here you can see a typical ocean crust with a lower Cretaceous section on top, seals, and then overburden. So there's another possibility for oil existing on oceanic crust. And then this is work that Jose Gorosabal has done using some 3D data from GeoX, but we can see the Cameroon volcanic line comes through here, and it sort of arches up a lot of the sediments in this very deep water oceanic setting. So this looks like another potential for structural traps along that line of volcanoes. Okay, so finally going back to Brazil. So now we're back to the Campos Santos, which is the sort of a transition between the volcanic margin south, which would be southern Brazil down to Uruguay and Argentina, and the non-volcanic margin, which would be everything north of Campos Santos. So it's somewhat of a transition, as we saw in, like, for example, in Guyana. And then over here, we've got Namibia, and it's definitely a volcanic margin. It's conjugate to Uruguay. So again, the colored dots for the different types of wells. The white line is the COB from Mueller. The red line is from our group. And zooming in a little bit on Campos Santos. So this polygon here would be, it's called the pre-salt polygon. It's basically the main production area in Campos Santos. This feature over here, this is the Merluza Graben, a failed rift. And then this feature here is the external rift. So the pre-salt polygon is a high that separates the two rifts. But notice, again, the colors, mainly oil here, a few gas wells here, and now exploration is focused on the external rift. There have been quite a few gas wells, particularly in this area, but a lot of it remains unexplored. So the question there is whether this could be a productive area in the very deep water part of Brazil. So again, I mentioned this transition between the seaward dipping reflectors. This would be down in like Uruguay, Argentina, and then we turn this corner, the Florianopolis fracture zone here, and we get into what appears to be a very narrow zone of volcanism. So this is starting to dissipate. This is work by with Beltran and Sharon Cornelius in this area. But again, very narrow zone here between the ocean crust out here and the external rift here, and then this would be the called the Central High and the Maluza rifts over there. But so looking at A, B, and C, you can see A is very big, broad SDRs. B is sort of a narrow zone of possible some magmatic activity, and then C is coming from Roos area, and there you can see some half gravens filled by either sediment or magmatic rocks. So that's what she's sort of working on there. And then just some other images from Roos area, courtesy of TGS. Lots of half gravens, coquinas, which can be very good reservoir rocks. There is some magmatic activity here, but there's also a lot of sedimentary rock. So this would be the potential for this area. And then she's done some 1D basin modeling for this area just to see what could be mature here. And using some of these sources, it does predict wet gas out here, which is consistent with some of the recent wells that have been drilled. Okay, so finally, I'll end on talking about Namibia, which is in southwest Africa. It's over here. You can see the COB, the white line, big discoveries. There's a lot of shallow gas in Namibia, the Kudu gas field, but then recently, the past couple of years, have been some big oil discoveries in the deepwater area. So just to zoom in on that a bit more, so the Kudu gas field sits up here, and these big discoveries are down in this area. And I think I showed this before, but they're sort of perched on the Venus trend is perched on this part of the SDR. And then there's another field at a higher level up. It's beneath this passive margin fold belt. You can see that's come down on top of it. So it's trapped right there. So there's a lot of prospectivity here, mainly through Aptian source rocks that are widely distributed. And then there's a lot of exploration going on now in the Pelotas Basin, and also in going into Uruguay. And one question to ask is how analogous is the Pelotas Basin to its conjugate in Namibia? They have some similarity. Like the Kudu gas field, there's a gas discovery up on the shelf. There haven't been deepwater wells in this part of the Pelotas, but possibly oil if it's similar to the Namibia analog. Okay, so I'm going to wrap it up there, but I just wanted to close on reminding everyone of these points, which were sort of the main talking points that I made for each of these areas. This would be the main sort of takeaways from the talk. And then just to point out what we're planning, so with our CBTH project, so we're kind of going through this loop, starting out with mapping. And for that, we depend heavily on our data providers like TGS and other GeoX. And from there, we get to a framework. So framework kind of refers to all the parameters that go into understanding the basin. Its heat flow, its crustal thickness, its overburden. And then we take all of those parameters, which we very carefully compiled, and we put them into Excalibur Basin modeling, which you saw an example of from Guyana. And then from there, we can compare it to previous wells, of which in some places there are a lot, other places not so many. But then we can kind of validate our model if there are a lot of wells. If they're not, our model has a lot of predictive power, so that can lead to discoveries. So that I'll close and open the floor for any questions.
Thank you. That was wonderful.
Okay.
So we do have a question we have from Salma Ahmed. You might read it in the question and answer. It says, is little salt and least amount of hydrocarbon associated with obliquely opened margin? So I think, what is the relationship between salt and hydrocarbon in an obliquely opened margin?
Okay. Let me go back to my salt slide. Sorry, I'm just
Excellent. Oh, and as you're going back there, I want to remind everyone that Jean-Marie Legel did a webinar for us on Excalibur, and it's archived. So I put a link to the recording in the chat.
Okay, but the question was.
Okay, so what is the relationship between salt and hydrocarbons associated with obliquely opened margins?
Well, in the Atlantic, these margins, so the salt here on the right is shown in red. So this would be Campos Santos, this would be Angola region. These margins open orthogonally, right? So oblique opening and salt weren't really connected there. Salt did not penetrate into the equatorial margin, which did open obliquely. So we don't really have any record of salt oblique opening in that region. As in these areas, these are all orthogonally open. So I guess my answer to the question is we don't really, as I can't think of a obliquely open rift with salt, at least in our study. I'm sure there are others in different parts of the world, but I don't know, is that
interesting? Yeah.
okay?
So Steve Naruk, if you're on the line, feel free to open your microphone and ask your question. I'm not sure what the question really is, but he remarks that the Niger Delta DW fold belt discoveries are consistent with your revised COV there.
Oh, that's good to hear. I didn't know that, but let me just go back to the Niger Delta. Yeah, so yeah, we're pushing the COB seaward to the red line, and we're not just doing it randomly. We're using the magnetic data. There's some seismic data in this region, but this is a very promising area because you can see there's a bunch of new discoveries lining up along Ghana, Ivory Coast. They extend back towards the Niger Delta, but there hasn't been a lot, as far as I know, a lot of recent drilling in the western Niger Delta. And the other area that we're interested in is the eastern Niger Delta for the same reason. But there, it appears the ocean crust does come a little closer. So maybe not as broad a zone as over here in the west. But I'm, Steve, if you have the information on those discoveries, I'd be happy to look at those because it is very relevant to what Jamoki's working on.
Yeah, we can discuss that offline. But the deepwater fold belt discoveries lie closer to your red line, just inboard of your red line.
Yeah.
Both for the southern delta and the northern delta.
But we're really looking at I would call it the downgoing plate. In other words, the delta has come out as sort of this fold belt, but we're really looking at the very distal end of that, where there's still rifted Cretaceous rocks fairly close to the surface and not necessarily covered by the fold belt, if that makes any sense. So this area here looks really promising because it looks like a kind of a broad rifted zone, very similar to Ghana, which has turned into a great place. Wherever you have these sort of bends, you get a greater amount of extension and you create these sort of triangular shaped zones, which I think are really interesting for exploration.
Thank you. Yeah. So I want to mention that Huyen Bui is in the audience, and I just want to thank her. She's the chair of the subcommittee for AAPG for OTC, and so I want to encourage people to attend OTC. We have a good technical program this year, and then especially Image, where Paul Mann and his team are going to be presenting quite a bit. So we have another question. This is a rather long one. This is from Stephen Getz. And Steve, if you want to open up your mic and ask and comment, you can. It says, offshore Senegal, there appears to be lower Jurassic Toarcian source rocks that were deposited in a rift graben, sandwiched between the COB to the west and the main continental landmass to the east. It appears that a somewhat similar situation exists in Guyana. Do you agree?
Let me just get back to a map that has both. So you mentioned Senegal, which would be north of the Guinea Plateau in this area, and then Guyana is back here. But could you repeat specifically what you said about Senegal? I didn't catch that.
Maybe Steve can if he's online. Yeah.
Can you hear me?
Yeah, go ahead. Yeah, go ahead.
Okay, yeah, I worked Senegal both onshore and offshore, and it appeared to me as though you had a lower Jurassic source rock. That source rock is actually in several areas along that West African margin. Most of the known source rocks occur in the Cretaceous section, but there appears to be a lower Jurassic source rock. There's indirect evidence on that on a well within the onshore area of Senegal. And it looks to be that source rock, and of course, lower Jurassic source rocks are kind of Toarcian of age, and usually they're limited to grabens. In other words, they occur within rift grabens. And I'm wondering if you don't have a similar situation to this over there in Guyana, because you have an onshore graben there, the Takadu graben, which does have some Jurassic source rocks, as I remember. There's not much in the way of production in that graben for a lot of different reasons. But you have the offshore equivalent of that same graben, and I'm just wondering if you don't have a deeper play offshore Guyana that people haven't addressed. If so, I would think it would probably not be Cretaceous rocks. It'd probably be in older Jurassic rocks.
No, oh, first of all, Senegal, you're right. That's the Central Atlantic, so that's the older Triassic, Jurassic opening. But like I was saying earlier, for Guyana, you're at the boundary, right? So you have both the Triassic, Jurassic, which is very obscure because it's buried under the later equatorial Atlantic rifting passive margin. And as shown here on the right here, remember, this is the Liza discovery. So Liza discovery is just in the late Cretaceous submarine fan reservoir. But below there, you have all of this earlier rift history, which is the Como 1 and the what we call the Guyana Rift, which no one really knows anything about and hasn't even been close to being drilled. Some people, when Liza was originally discovered, thought the source might be coming out of one of these rifts, but since then it's been proven that the source for Liza and all the discoveries in Guyana so far is the Cenomanian-Turonian CT source rock, which is much higher. It's called the Conjay Formation. It will be just beneath this submarine fan here. Oh, here it is here. So it's this interval, Conjay. So yeah, I think you're right. The problem with Guyana is that it's just so much sediment, I guess, that no one has really dive down and try to look very deeply at the part that comes before all the late Cretaceous and the Cenozoic. So does that answer your question?
Pretty much. The problem with going for a deeper play below these Cretaceous sands is the economics, because you won't be making an oil play. You at best are going to be making a gas condensate play. And when you go to a gas condensate play in deep water, all of a sudden you're back in Namibia, whether you wonder whether by the time that you deal with a pressure maintenance problem associated with gas condensate production, because you got to drill maybe at least one well out of every 3 or 4 has to be a recharge well to solve the condensate banking problem. And that would probably be the same problem you'd have here. Although there have been some wells drilled, I think, on the Demerara Plateau that had some hydrocarbons in it.
Yeah, no, there have been shows on the Demerara. Of course, the Demerara is a very different thing, right? It's basically a sort of late Jurassic SDR pileup related to what we were saying was a hotspot. So it's a very different sort of crustal framework than the rest of Guyana.
That's interesting. Okay. We have time for 2 more. So Lino Teixeira asks, is there a similar analogy between Suriname, Guyana, and the Amapá coast in the east margin of Brazil?
Amapá coast.
That's near the Amazon.
Let me find a slide. I mean, so Amapá is near Foz Amazonas, or where's that exact? I'm not 100% where that's located.
Yeah, it's near that delta area of the.
Okay, so in here. So the question is there a similar transition between volcanic and non-volcanic in the Amapá area? Is that the question?
Well, just an analogy between Suriname, Guyana, and Amapá and East Margin, Brazil.
To my knowledge, if it refers to volcanic margins, I mean, to my knowledge, like I was saying, Demerara is a very localized volcanic margin related to what we think is a hotspot. As far as I know, down here, there are no volcanic margins. So I would say maybe not a good analog to Guyana. I mean, here it's an obvious transition from volcanic margin in Suriname to non-volcanic in most of Guyana. But here I'd say probably not a volcanic margin anywhere near this place. If that answers the question.
Okay, thank you. Oh, it looks like Gerardo Gaitan has his hand up. So if you'd like to ask your question.
Sure. Hi, Professor Mann, Gerardo speaking. Just a quick question germane to the modeling that you have for the Guyana-Surinam basin on the Demerara Plateau. I was just wondering what type of heat is this model taking into consideration? This is not radiogenic heat, is that correct?
Right. Well, the radiogenic heating is a major contributor, but there's other factors like the thickness of the overburden, for example, which is in this kind of area where a lot of the discoveries are made. But I'd say most of the heat source would be the rocks beneath here, which, as you can see, the continent ocean boundaries here. So this would all be rifted continental crust. Here you have an oceanic plateau-like feature on rifted continental crust. All right, so you'd have some more complex heating related to that.
I see. The reason why I'm asking is because I had in mind that, and I will share that if I find it. The paper, I don't remember by who, but basically that the continental crust and basin floor are non-granitic and, if I remember correctly, non-generated radiogenic heat. So this is a little bit incongruous to what I'm thinking about. I might be.
Yeah, well, of course, we're talking here about the Guyana Shield, which is pretty complicated, but it does have its share of granitic rocks, along with a lot of other things. And it would be impossible to know exactly what those rocks are beneath this part of the rifted margin because they're deeply buried. But I think there are plenty of maps of the Guyana Shield where you can get some appreciation for the different rock types that are there.
I see. Thank you.
Okay.
Thank you. That was a great question. Okay, so we have time for one more. And Emmanuel Biondi asks, he said, thanks for the presentation. And what suggestions do you have for the best modeling petroleum systems with complex thermotectonic patterns and heat flow histories in magma-rich contexts like Namibia?
Well, the kind of standard package is Petromod, but I think the more sophisticated and more detailed model would probably be Excalibur. And you might want to reach out to Jean-Marie and talk to him about that, because like what we've been doing, like what Kenneth's been doing in Guyana, is really fine-tuning the parameters that go into the model. And with Petromod, there's just a lot less parameters that you can sort of introduce into the model, or they're sort of fixed, So I would suggest maybe talking to Jean-Marie about that and some of the advantages that Excalibur might offer for that.
Yes, that's a good idea. So I want to mention to everyone again that you will be getting an email with a link to the recording of this presentation. It'll take a few days for me to process everything. And then you'll get a link to our upcoming webinar with Andy Pepper. And also I put a link to the recording with on Excalibur in the chat. So,
well, sorry,
yeah.
I'd just like to add, you know, a lot of what I said today are in these publications. There's a Encyclopedia of Marine Science talking about Passamar. There's these two papers are in this volume edited by John Rothstein called Deepwater Sedimentary Systems, which you can get on Amazon or other places. Or if you want, just send me an email and I could send you these PDFs. Some of these are on my ResearchGate or academia sites, so you can try to download those. If that it doesn't work, then just send me an email and I can send it to you.
Well, that's great. And also I would encourage people, if you have, if you're part of a university, you can log into databases and there are different Geoscience World and all those databases have these and Science Direct. So thank you. And I want to thank our sponsor, NewTek, again, and NewTek Energy. Have generously made it possible for us to offer this for free and to archive it. And so I want to thank you. And then, Paul, if you'd like to talk a little bit about the research that you are looking forward to doing in the near future and maybe presenting it image, that would be great.
Yeah, our group will be at Image. I think we have 8 or 9 abstracts submitted. And a lot of these areas that you just heard about, Niger Delta, Campos Santos, Uruguay, we will have presentations at Image, and there you can get the latest on that. I just gave you a very brief sort of overview, but if you wanted to follow up, yeah, look for us at the Image presentations, either oral or posters.
Fantastic. Well, thank you, everyone, and want to thank you again for attending. This has been a very, very informative and absolutely fascinating presentation. So I want to thank you again, and we'll be in touch.
And thank you, Susan, for organizing. A great job and great turnout. So I really appreciate that.
Thank you.
All right.